Hi Year 11s, welcome to this video on compound interest. I apologize that I'm not there with you in person today. The reason for this is that I'm attending the Physics Teachers Conference. So I hope that this video will be enough to get you going, and you will need to read the textbook to fill in some gaps. So my advice is not to worry about writing down everything that's in this video, because I will upload the completed version of these notes. So you can write down just what you need in your own time. I would rather that you just sat back, relaxed, and focused on trying to understand the content of this video. So let me emphasize again, don't worry about writing everything down because you'll have access to it by the time class is in session. So let's get underway. Let's start by defining a geometric sequence. We've already done this many times. To define a recurrence relation, we need two equations. The first equation tells me the starting number, which I will give the symbol A. The second equation tells me how to get the next number, Vn plus 1, from the previous number, Vn. And the characteristic of a geometric sequence is that the next number is found using multiplication. Furthermore, we multiply by the same number, which we call capital R, the common ratio. And A is just the starting term, or the initial term. So, in this exercise, we make a distinction between different kinds of geometric sequences. Sometimes the numbers go up, and sometimes the numbers go down. So we're going to use the word growth to mean the numbers go up, and decay to mean the numbers go down. A more formal term would be the words increase and decrease. So, in order for this to happen, let's start with increasing or growth. This happens when the value R is bigger than 1. So from your experience with maths thus far, you should be familiar with this idea that if I multiply by 1, nothing changes. But if I multiply by a number greater than 1, the number is going to grow. Similarly, if I multiply by a number that is between 0 and 1, what's going to happen is the number is going to get smaller. So I'll write this in words just so that it's clear. R is greater than 1, and R is between 0 and 1. Not inclusive. So we're not including 0 or 1 in this instance. I know this is a bit abstract, so let's make this concrete with an example. So have a look here. In this first example, my common ratio is 4. Notice that the number 4 is bigger than 1, so this is going to define a sequence with geometric growth. And if I were to give a reason, I would say since capital R, my common ratio, is 4, which is greater than 1. All right, next example. In this second sequence, my common ratio is 0.75. This number is between 0 and 1. So this time, the recurrence relation is going to define a sequence with geometric decay. Since the common ratio, capital R, is 0.75, which is between 0 and 1. And finally, I'd like you to consider the third sequence defined by the recurrence relation v0 equals 5 and vn plus 1 equals vn plus 4. This one, it's actually not a geometric sequence. It's an arithmetic sequence. So when you do question 1 from the textbook, it's going to ask, does the sequence have geometric growth, geometric decay, or neither? And in this case, the sequence has neither behavior. So neither geometric growth nor geometric decay, since it is an arithmetic sequence. So recall, if you've forgotten, in an arithmetic sequence, we add the same number each time. In a geometric sequence, we multiply by the same number each time. If we're not multiplying the same number each time, as we are not in this particular instance, we can't speak of geometric growth or geometric decay. All right, so in this exercise, we're going to use geometric growth to model something called compound interest, and we're going to use geometric decay to model something called reducing balance depreciation. In this video, we're just going to focus on the first application, which is compound interest. This video is probably going to feel a bit heavy because the content is more challenging than some of the other exercises. So don't feel bad if you don't understand it straight away. In my experience, I've found that it takes most people a few lessons to get their head around all of this. So just sit back and try to take as much in as you can. And remember, you'll be able to read these notes later. All right, so let's define compound interest. Here's my definition. Compound interest is a situation where the value of an investment increases by the same percentage each time period. And this means interest payments are recalculated each time period. If you've been paying attention in this topic, this should sound different to simple interest, which was the other type of interest that we studied. In simple interest, which we modeled with arithmetic sequences, the interest payments were fixed and do not change. Over time. So, one thing I want you to remember as we begin our study of compound interest is if you're dealing with simple interest, you should use an arithmetic sequence. If you're dealing with compound interest, you should use a geometric sequence. One of the things that I've found when marking tests over the years is when students are still learning the difference between these two types of interest, they tend to use the wrong sequence. So in this exercise, you should only be using a geometric sequence. You should not be using an arithmetic sequence. So just keep that in mind. Okay. So I just want to give you a feeling for how these two things are different. So let's consider an example where we open a bank account with $1,000. And I tell you that the account is going to earn 5% per annum. And remember, the word annum means year. So this really means interest is paid at a rate of 5% per year. Furthermore, we're going to make payments once per year. So if we did this calculation for simple interest, we would start by finding 5% of 1,000. And if we do that calculation, we get 50. So what would happen in the case of simple interest is we would add 50 at the end of the first year. But we would not change this amount. We would add 50 in the second year, in the third year, and in the fourth year, and so on. In the case of simple interest, the payment is determined entirely by the amount at the beginning, which isn't very good. Because if I let this run for many years, the interest is going to be very small compared to the amount in my account. Compound interest is kind of a better deal for you. So instead of finding 5% of 1,000 and doing that calculation once and using that same payment each time, compound interest literally compounds the interest. It recalculates the amount. So instead of finding 5% of 1,000 and applying that every year, what we're going to do is find 5% of 1,050 and then add that. And then 5% of 1,102 and then add that. So between these two accounts, I hope you can see that if you're the one who has the money, you would rather have the compound interest account. And this is how bank accounts work in the real world, and this is how bank loans work in the real world as well. So compound interest is really the real world. We teach you simple interest first because it's helpful for understanding compound interest. So simple interest is the same payment each time. Based on a percentage of the amounts at the beginning. For compound interest, we recalculate the payments each time. And if you're the one getting the money, that's good news. What we want to do in a moment is use the language of recurrence relations and rules to do this simply. So let me just briefly recap what it means to increase a number by a percentage. I actually wrote this on the whiteboard on Thursday before we headed off for school photos. So there's no need to get it down again. But just by way of reminder, to increase a number by some percentage r, what we need to do is take that number and multiply by the factor 1 plus r divided by 100. We don't actually need the brackets, so I'll get rid of them, but when you type this into a calculator, you will want to enclose the whole thing with brackets. So for example, suppose I give you the number 80, and I want to increase this by 20%. The calculation that we would do is 80 times brackets 1 plus 20 over 100, which is the same as 80 times 1.2 if I evaluate the bracket first, and that gives me 96. It will be easier in the long run to do percentage increase using this formula rather than a two-step calculation which you might be used to in previous study. Because this is what we will use in our geometric sequence. This is going to be our capital R. All right, so let me tie this together with just a little bit more theory, and then we'll do two examples, which I hope will make this really clear for you. So the common ratio, which is capital R, in our recurrence relation, I'm going to divide this into two cases. So if you are receiving compound interest and the payments are made once per year, then the common ratio you want to use in your recurrence relation is 1 plus R divided by 100, where R is the annual interest rate. So for example, if it's 5% per year, then R equals 5. Now there's another case. Suppose I told you that interest was paid more than once per year. This is actually what happens in practice, because we don't want to wait a whole year to get our payment. It's more common to have interest compounded every month, every week, or even every day. So what I'm going to do is I'm going to say, if interest is paid P times per year, where P could be any number. So for example, if it was quarterly, that would mean P equals 4. There are 4 quarters in a year, or 1 quarter being 3 months. If interest was paid monthly, then P would be 12. If interest was paid weekly, P would be 26. Sorry, 52. And if interest was paid daily, P would be 365. In this case, if we want to develop a recurrence relation where we are compounding more than one time per year, we just need to make a slight adjustment to our common ratio. And here we're going to use 1 plus R divided by P, all divided by 100. Okay, I know that formula looks really weird, but that's the same formula that's used in your Year 12 textbook, and I'm introducing it to you now. Think about it this way. Suppose the interest rate was 8% per year. If I've split that into quarters, that will be the same as saying 2% per quarter, since 8 divided by 4 is 2. All I'm doing is I'm taking my annual interest rate and splitting it up evenly into each smaller time period. So, with this in mind, let's do a couple of examples. I know there's a lot here, so I'll summarize the most important parts. Suppose I open a bank account with $1,000. The rate is 5% per year, and interest is paid once per year. I'm going to define Vn, so a sequence, to be the amount in the account after n years. So at the start, it's V0. After 1 year, V1. After 5 years, V5. After 10 years, V10. The first question asks for a recurrence relation. So here we go. V0 is going to be the amount in the account before any interest is earned. And that number is 1,000. Sometimes there is a 1-mark question on the Year 12 exam just for that. Okay. Next, we need to define a geometric sequence with a common ratio, capital R. So I know that Vn plus 1 is going to be some number times Vn. But what number should I use? Well, the annual interest rate is 5%. So I can write lowercase r equals 5. And my common ratio, capital R, based on the formula on the previous slide, is 1 plus R divided by 100. So that's the same as 1 plus 5 divided by 100, or 1.05. And that's where that number came from in that page where I compared simple interest and compound interest. So here's our recurrence relation. V naught equals 1000, Vn plus 1 equals 1.05 times Vn. And that's actually the hard work. Once we have this, parts B and C become very simple, provided you've understood the work leading up to this lesson. So, part B, find the amount in the accounts after 10 years. So what we want is V10. In order to do this, I'm going to use a rule. So I'll write it one more time, because I know that you are still learning this. If V naught equals A, and Vn plus 1 equals R times Vn, then a formula for Vn in terms of n is Vn equals R to the power of n times A. So, in this instance, A is 1000 and R is 1.05. So my formula for Vn is 1.05 to the power of n times 1000. And at this point, now I can substitute n equals 10 into this formula. So now I need to find 1.05 to the power of 10 times 1000. And that gives me 1628.8946. Now, we live in a world where money transactions are made usually to 5 cents with cash in Australia, or to 1 cent if we are using electronic banking. So in general, if you're not told otherwise, the advice I would give you is to round to the nearest cent. In this case, my third decimal point, 4, is smaller than 5, so I'm going to round down to 1628.89. And there's my answer. So, think about this for a moment. I open an account with $1,000 and I earn 5% per year for 10 years. If this was simple interest, I would expect $1,500 in my bank account. But here, I've actually got much more than $1,500. I got $1,629. Compound interest really makes a difference, particularly over long periods of time. All right, part C. How much interest is earned in 10 years? This is not going to be the same as our answer to part B. What's being asked here is how much has the amount grown by in 10 years? What we want to do here is find the difference between V10 and V0. That is the difference between 1628.89 and $1,000. And this is a straightforward calculation. The answer is 628.89. So we earned $628.89. Okay. Let's do one more example, and then we'll be done. Okay, here we go. You'll notice this question is almost identical. So we start off with $1,000. I've actually just noticed a problem with this question. I'm going to change this to 4.8, just because it's going to make it much easier. So I'm just going to change this to 4.8% to avoid some issues with terminating decimals. So $1,000, 4.8% per annum. Interest is paid once per month rather than once per year. And I'm going to say VN is now the amount in the account after N months rather than N years. Okay, so first step, we are asked to find a recurrence relation to define the sequence Vn, the amount in the account after n months. Well, as always, we start with V0, the amount in the account at the start, which is 1,000. And because this is compound interest, we're going to use a geometric sequence. So I need to define Vn plus 1 to be some number, which I don't know yet, times Vn. The question is, what is that number going to be? Well, the annual interest rate is 4.8. So lowercase r is 4.8. And then, using the formula I gave you for P times per year, there are 12 months in a year. So P equals 12. And the common ratio, capital R, is 1 plus R divided by P divided by 1,000. Well, divided by 100, sorry. So that's going to be 1 plus 4.8 divided by 12 divided by 100. And that's going to be 1.004. If I used the number 5 here, this would be going on forever, and I wanted to avoid that. So here's our recurrence relation. V0 equals 1,000, and Vn plus 1 equals 1.004 times Vn, using this formula here to get capital R. Okay, part B. Find the amount in the account after 10 years. Now, there is a trap here. The trap is, if you're inexperienced, you're probably going to try to find V10. Now, the problem with doing that is V10 is now the amount in the account after 10 months, not 10 years. So we need to remember that 10 years is 120 months before we do this question. Okay? So we actually want to find V120 rather than V10. Because now my recurrence relation is defined in terms of months rather than years. So once we've remembered that, we can proceed as we did with the previous question. We start by writing a rule. Vn equals 1.004 to the power of n times 1,000. Which means V120 is 1.004 to the power of 120 times 1,000. You definitely want to use the rule for this because you don't want to be pressing times and enter 120 times. So let's go ahead and do this calculation. So it's 1.004 to the power of 120. And the answer is 1614.5278. And this time, the third decimal point is larger than 5. So we are going to round up to 1614.53 to the nearest cent. All right, and the interest earned is V120 minus V0, which is 1614.53 minus 1,000. And that gives me 614.53. As an exercise, I invite you to compare 4.8% per annum paid monthly with 4.8% per annum paid yearly. You should find that compounding monthly gives you a slightly better return than compounding once per year. Maybe we'll do a do now in our first lesson next week, making that comparison. All right, you've done really well to listen up until this point. You'll be glad to know that we're done with the video now. So I'm assigning exercise 3H, and I'm assigning these specific questions here. So don't worry about questions 3, 10, 11, and 12. Don't worry about depreciation, because that's going to be covered in the next lesson. I know this was quite a heavy lesson, so if needed, I can give some time next week to catch up on this. But I would still like you to complete as much of exercise 3H before next Wednesday as you can. When you come back for your second class, I will cover the remaining questions on depreciation. All right, thanks everyone, and I'll see you in the next video.